All right, let's jump right in. Welcome, everyone. Today, we're getting you completely ready to absolutely conquer discrete dynamical systems on your linear algebra exam. You know, if you've been staring at matrices and vectors, kind of wondering how these abstract numbers actually apply to the real world, well, you are in the perfect place. In this explainer, we're going to break down the core mechanics of how systems evolve over time, giving you the exact tools you need to ace this topic. So, have you ever wondered how we can actually mathematically predict the future? We're starting with the big picture here, predicting incredibly complex systems like traffic flow, biological populations, or even economic markets using math. It kind of sounds like a superpower, doesn't it? The whole core idea is that a system is simply any entity whose state changes over time according to a specific rule. If we can just understand its present condition and figure out that rule of change, we can literally calculate what that system is going to look like tomorrow, next year, or even a century from now. Now, real life, it feels continuous. But to actually compute it, we have to use discrete snapshots. Think about it for a second. Continuous systems evolve smoothly, without any breaks, kind of like water flowing continuously out of a tap. But trying to model that mathematically can be ridiculously complex. Discrete systems, on the other hand, only change at clearly defined time intervals. By discretizing the system, we make our analysis computationally tractable and, honestly, mathematically elegant. We aren't trying to look at every single microsecond, we're just looking at specific measurable steps. Okay, here's our game plan for this explainer. We're going to define what a dynamical discrete system is, establish discrete time steps, interpret the state transition matrix, predict long-term behavior, and finally, finish up with a solid exam review. Section 1. What exactly is a discrete dynamical system? Picture this. Imagine you've got a camera snapping photos of a busy highway every 5 minutes. That gives us these mathematically elegant, perfectly defined time intervals. Instead of watching an overwhelming, continuous video of the highway, that camera gives us observation 0 at 7 a.m., observation 1 at 7:05 a.m., observation 2 at 7:10 a.m., and so on. Each interval represents a very specific point, which we call T sub k, where we just measure the state of the system. This is what makes tracking massive amounts of data entirely manageable. Moving right along to Section 2, defining our discrete time steps. So we have to translate those physical camera snapshots into actual math. We know what our intervals are, but how do we represent the stuff we're measuring at those exact moments? Well, the physical reality of a traffic intersection becomes our state variables. These represent things like traffic density on streets A through D at any given discrete time step, which we call K. We take all these variables and organize them into a single column vector, the state vector, denoted as x of k. So the top number in our vector, x1, is the traffic on street A, the next one down, x2, is street B, and so on. This state vector is a pure numerical snapshot of the entire intersection at one exact moment in time. All right, Section 3, the state transition matrix. Now for the core math. And listen up, because interpreting this is a massive focus for your upcoming exam, the state transition matrix. We have our snapshots, right? But how do we actually connect them? How do we move from the present into the future? You need to think of matrix A as the absolute rule. It's literally the engine driving your system forward from one step to the next. It is a square matrix, meaning n by n dimensions, and its entire job is just to take your current state vector and mathematically transform it into the next time step state vector. If you understand matrix A, you hold the key to the entire dynamical system. The formula, x of k plus 1 equals matrix A times x of k, is essentially a little three-step machine you just run over and over. You take your current state, x of k, you multiply it by matrix A, and boom, out pops your next state, x of k plus 1. Want the state after that? No problem. Take that brand new vector, plug it right back into the formula, and multiply by matrix A again. It's just a continuous, repeating cycle of multiplication. When you actually plug the numbers into matrix A, it becomes perfectly clear how these state variables evolve at every discrete time step. For example, at time step 0, let's say we start with values of 10 and 5. After running it through our transition matrix engine just one time, our new state vector becomes 5 and 4. Run it again for step 2, and it shifts down to 2.5 and 3.2. We are actively predicting the evolution of this system, step by step by step. Which brings us to Section 4, predicting long-term behavior. Okay, we are now at a totally crucial exam topic. What happens to this system as time approaches infinity? Calculating steps 1 and 2 is just simple arithmetic, but I guarantee your professor is going to want to know the ultimate fate of this system after 50 steps, or even infinitely many steps. Here is the secret. You absolutely do not need to calculate 50 individual steps. You just need to look at the eigenvalues of matrix A. By diagonalizing our matrix and finding its eigenvalues, which are represented by the Greek letter lambda, we can instantly see the long-term trajectory. Because calculating future states means we're essentially raising these eigenvalues to the power of k. The size of lambda completely dictates whether our system is going to shrink, grow, or stabilize over time. Let's look at the 3 specific cases you need to know for the test. Let's analyze scenario 1, where both eigenvalues are less than 1. Say 0.5 and 0.8. Just think about the basic math here. What actually happens when you multiply a fraction by a fraction over and over and over again? Well, because the eigenvalues are fractions, the values shrink, eventually crashing the entire system down to 0 over a long enough timeline. Regardless of where your initial state starts, the curve just flattens out, driving both x1 and x2 towards 0 as time approaches infinity. The system essentially decays into nothing. Next up, what if we have a mixed condition? For example, lambda 1 is 1.1, but lambda 2 is 0.8. So here, one eigenvalue is greater than 1 and the other is a fraction. In this scenario, x1 dominates and grows very large, while x2 slowly fades away to 0. The part of the system tied to the 1.1 eigenvalue compounds and explodes upwards, while the part tied to the 0.8 eigenvalue just decays. It's basically a mathematical tug-of-war, where one variable completely runs away with the system and the other just diminishes entirely. And finally, consider the third condition. This is where both eigenvalues are greater than 1, like 1.1 and 1.05. In this case, every single time step acts as a multiplier that increases your total value. So, in this third scenario, both variables continuously expand, making the system grow absolutely massive as time approaches infinity. Because you're repeatedly multiplying by numbers larger than 1, the values just shoot up and to the right. The trajectory is entirely unbounded. There's no decay happening here at all. It's just pure exponential-style growth for the entire system. All right, let's wrap it up with Section 5, Exam Review and Key Takeaways. Let's distill this down to the absolute essentials you must have memorized for your test. If you internalize this summary, you're going to be in fantastic shape. Keep these points highlighted in your notes. Remember, we are dealing with discrete intervals, snapshots in time. Your current snapshot is your state vector, x of k. The magical formula to find the very next snapshot is simply x of k plus 1 equals matrix A times x of k. You have to deeply understand that matrix A is the absolute engine of evolution for your system. And finally, when a question asks for the long-term, infinite behavior, do not start multiplying manually. Just find the eigenvalues. They will tell you immediately whether the system decays to 0, exhibits mixed behavior, or grows unbounded. So, by translating absolute chaos into nice, neat, predictable matrices, what other futures could you mathematically model? Keep wondering about the immense power of linear algebra to explain our world. Because once you master interpreting that state transition matrix, you aren't just solving a math problem on a test. You're literally looking at the fundamental code that can predict stock market fluctuations, the spread of rumors, or even the density of traffic on your drive home. It's all connected by these discrete mathematical steps. You've got this. Best of luck on your exam and have a great study session.